here. Um, Ears good?
That's great. Yeah.
That's sort of like the analog, like fixing what the land keeps doing.
All right, let's have our seats in preparation for the next lecture. Do you want to introduce
I was just going to say I was just going to tell about the coffee machine.
Okay, you can tell them now.
Okay.
If you do, I can do the introduction.
All right, welcome back, everyone. Just note about the coffee machine that appeared outside. You may have noticed there's a coffee machine now. That was set up for the department. Just happens to have appeared during TASI. It's free right now, but the price of it being free is feedback, which they'd appreciate. So we're already providing coffee for all of you, but if you have feedback about the coffee, I think you can just let us know, send me a message or leave something on Slack, and I'll convey it back to the people who run the machine. I think they would appreciate that.
All right, you ready, Simon?
All right, so we're very happy for our next lecture to have Simon Caron-Huot, who's going to tell us about causality constraints on EFTs and gravity.
Yeah, so hello everyone. It's great to be in this full room. Yeah, so I'll be giving a few lectures on the main theme is causality. And when I was preparing this, I was reminded of Sidney Koseman's famous lectures on acausality, which starts with, please read these notes by last week, which is hard.
Is the mic on?
This one is on.
Okay, I couldn't see the light.
Okay, good. You hearing well? And well, actually, there's no type notes for these lectures, but that's not going to help you to read them by last week. So these lectures were about situations where this basic fact that the past influences the future, but not the other way around, and situations where you get equation of motion, where you have the equations seem to tell you the opposite unless you impose some interesting boundary conditions. So anyway, so I will not be talking about this type of causality in these lectures. This lecture will be about relativistic causality, which is more precisely this notion that we cannot, should not be able to send signal faster than light. Okay? Put it in quote. It is still a relatively vague statement. What do I mean by signal? What do I mean by light? But it's deliberately vague, but we try to make sense of it. There are situations where it's very clear and situations where it's not completely clear, including gravity, for example. Yeah. So yeah, what is going to be relevant for the sort of general motivation or philosophy of these lectures that these types of constraints are useful for certain non-perturbative approaches, so-called bootstrap-type techniques, where we try to constrain some partial models of interest or general space of theories, one or the other, in terms of general constraints like causality or things that we know must be true by the theory. Sasha Zhiboydov will talk much more about the actual constraints. It's also useful for perturbative techniques. A lot of modern techniques to calculate scattering amplitudes, for example, use ideas of breaking amplitudes into parts that really use these basic principles or sways. And actually, Sebastian Misera will talk a lot about this. It's just a general motivation. And I think the sort of more broader motivation. So I'll be providing a kind of more can I say the sort of more conceptual overview of these ideas and why causality is important and useful and what we can do with it, and providing you with some back of the envelope calculations you can do and ideas like this, then more the advanced calculations that would go in these other lectures. So I think another general motivation is that the theories that we want to study and that describe the world are actually very constraining, and there's been a lot of progress recently in using path integral techniques, and we have great lectures about this. But it's possible to use the path integral to study theories that are very not sensible. So the path integral doesn't tell you what theories you should study and what theories you should not study. And it's good to have some kind of other perspective on that. And I think the sort of particle physics viewpoint on what theories are interesting to study is good to talk about. Okay? So that's the which theories are sensible to study. Of course, nobody prevents you from studying a theory that violates these principles, but you should know what to do. Okay. Yeah. Part of these lectures will be based. The lecture will be mostly based on some, not so closely, but on some classic papers. So there's some interesting kinematical paper by Kenyamid, Wang, and Huang, 1709.04891. And actually, we'll be mostly talking about chapter 2 and 3. They do a two-dimensional story, but we'll talk about the general d-dimensional one, sorry, the four-dimensional space-time, and we'll talk a bit more generally. Talking about also another source would be a paper by Kamano, Edelstein, Madasena, and Zhiboydov, 1407.5597. And again, we'll be talking about the very chapter 2 and appendix D mostly of that paper. Yeah, so the general outline is this. So today's lecture is meant to be a kind of a broad introduction about why you should care about causality constraints, why it's constraining, and a general introduction to S-matrix ideas. And what does the scattering amplitude for gravity look like? How do you read it? What physics do you see from the formulas? And then we'll discuss more mathematically. So the way we actually use causality in practice is through analytic properties. But as soon as you start saying analyticity, people say, oh, just like something technical math thing. So I really want to make this physical connection very clear. And then we'll actually talk about dispersion relation, which is the engine of these applications. Okay. Yeah, and please feel free to interrupt. There should be plenty of time in these lectures. Okay, so the first thing I try to do is convince you that this notion that we cannot send signal faster than light is very powerful in terms of explaining the world around us. I think it's one of the most powerful ideas in physics. That's not a light statement. So I start by drawing a cartoon that, will be the x and the y direction. I'm going to show the electric field of a stopping decelerating charge. Okay? Yeah.
Can you say something about like how would one distinguish locality from causality like this, or is there like a different notion?
Yeah. So the main thing which has power. Oh, yeah. So the question is about exactly how locality and causality and all these concepts show up. The thing that I'm really going to use and introduce in a second is this concept that I don't want instantaneous action at a distance. So it's sometimes called like that, yeah. So this is really that partial notion, this relativistic causality is no instantaneous action at a distance. Okay? So let's see why this is extremely constraining when you're trying to make theories of the world that comply with that. Okay? So imagine you have a stopping electron, stopping charge. Okay? And this is a calculation you can do in classical electromagnetism, and in fact, you might have seen the graph I represented from E&M textbooks. And what you can do is you can plot the electric field after the charge has stopped. After the charge has stopped, you will have some electric field that points away from the origin. I'm going to write it like this. So this is the electric field, and this is the new field. Okay? However, the information about the fact that the charge has stopped does not propagate instantly throughout all of space-time. And if you go far enough from the charge, what you see instead is the old field. And the old field has this property that it's pointing toward where the electron is going to be. So at some later time, you'd have some old field, which instead is pointing in some other direction. So you have the new field, and you have the old field, which are pointing in different directions, and may have slightly different magnitude, and so on. And what separates them, when you solve the classical equation of E&M, is some kind of shell that move at the speed of light, ct. Bye. Yes, but I don't know how to do that. I understand what happened. This got stuck in this, and let me just move this. Okay. And back. Hopefully, it should be back.
Is that better?
Okay, thanks. Right. And so in between, you have the radiation. I tracked down this picture from a chain of reference in textbooks, and it's actually appeared in a book by J.J. Thomson in 1903. It's a very classical picture. So the whole book is about like phenomenology of like how do you manipulate charge, and then there's this paper doing the fundamental theory of radiation. So what the picture explains is two things. The first, it explains that whenever there's a force between two objects, so the electric field, it gives a force. Whenever there's a force, any force, a force can be affected by accelerating an object. And if you accelerate an object, the force has to change, but it cannot change it cannot change instantly everywhere. So there'll always be a radiation front that tells the world that the force has to change. So whenever you have any force, you need wave to propagate. This wave basically means that there's some kind of field that you can use to describe the wave. So that's why all forces in nature are associated with fields that emit wave-like solution. And this wave really have to carry energy, because if I put here a test particle, this electric field here can give a force, and force carries electric energy and momentum. And therefore, the wave that changes the force has to carry energy and momentum. So you really need this thing. And in the quantum theory, the energy and momentum has to come in quantized unit. So these are actually particles. Okay? It's basically one quantum of energy of the field. Okay? so the particle physics philosophy is like, when you talk to particle physicists, we're kind of obsessed about explaining the world by exchanging of particles. But like, the reason this has to work is this principle that if you cannot have instantaneous action at a distance, you have to be able to understand all interactions by exchanges of particles. Okay? It's a very, very powerful argument. Maybe I can say a bit more about this. So I mentioned that the radiation exists to tell the world that the force must change. And there's a very quantitative statement. There's a particularly nice quantitative statement of this in the context of gauge theory, which is that, roughly speaking, the time integral of the radiation is equal to the change in the Coulomb field. And that is the soft theorems that Anna Maria will talk a lot about. Okay? But there's a very general statement that's a bit more general than the soft theorems, which is that all forces can be mediated by fields. And that is why we try to understand forces by drawing Feynman diagrams. So we can try to understand interactions by. Is it a good time to raise the bar? I just want to draw a little picture here. So if time is going up, maybe I can just raise it a little bit for now. So we have an interaction. You have some particle following some trajectory. So this looks like a photon. Let me draw it a bit more. There's one particle that's following some trajectory, maybe because of some force acting on it, and I want to compute the force acting on some other particle. The claim is that I can understand this force by asking for the amplitude for this guy to emit the photon, and then this guy to absorb it, and then multiplying this ingredient by some propagation of the photon from one guy to the other guy. Okay, so relativist causality tells you that you have to be able to understand all interactions in terms of these basic building blocks, where you have some 3-point vertex that describe the emission and absorption of radiation. And it's very powerful because these 3-point vertices are basically uniquely fixed by Lorentz invariance up to a few parameters. So the list of interactions you can have is very restricted. Okay. That's what we'll discuss. Yeah. It's because, yeah, try to get used to it. Yeah, so the question is why causality highlights the importance of the 3-point vertex is that something has to be emitted and absorbed. And yeah, so classically it would be a wave. But the important thing is that these two guys cannot interact directly with each other. They have to interact through a field. So you create an excitation in the field, and then that gets absorbed on the other side. Okay? So the elementary thing is not this 4-point vertex, which is very non-local, but it's the 3-point vertex that builds this. A 4-point vertex will describe, will add some extra degree of freedom that only matters when the trajectories hit each other. Questions? Yeah. 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 So the question is about Yang-Mills, where the 4-point function is also important. The thing is that the 4-point function in Yang-Mills is not a free parameter. It only exists to fix some issue with this diagram that will. Yeah, when it's only internal, yeah, you have to use the concept like gauge invariance. We give examples where the photons are on the outside. When the gluons are on the outside, it really just fixes the statement that this is actually my next topic. Sorry, it's come later. So when you say that we have so if you think about the kinematics of a gluon you will say it's in perturbation theory is a massless spin 1 particle, right? And massless spin 1 means that it can have two transverse polarizations and no longitudinal polarization. So the 4-point vertex is just finely tuned to cancel the longitudinal contribution to this diagram. So it has no new free parameter in it in that sense. Okay.
So can I ask just before this, you gave a chain of logic for why all forces have to be mediated by particles.
Yeah.
But it seems like the argument was for all forces generated by something that stops. Like why would like a just stopped particle itself can also generate a field and then it will have
Yeah.
forces mediating?
Yeah, it can be stopped, but more generally here, whenever any particle accelerates, it gives you radiation that changes the field. Yeah. So you can imagine. So the question is, how do you go beyond the situation of a field that's stopped to understand the full force? And one tough experiment you can do is you can imagine from particles that are very, very far from each other, and then there's basically no interaction between them. And then you accelerate them and gradually bring them together. So then you can get the force, the total force that will be between them by integrating the radiation from the past. Because the radiation tells you how the force changes. Yeah. So it doesn't just apply when to stopping charge, but it's very general.
But see, maybe my confusion is more. I agree that radiation tells you how the force changes.
Yeah.
But without the change, also there is a force that has to be mediated. Right? There's no you can have a fixed charged particle there, and that there is no force change.
Without this tough experiment that I described, which start from a case where the force is 0 because the things are very far, I don't know how to get the integration constant. Yeah. Yeah. I haven't defined radiation, what I mean exactly by radiation here. There's some gauge-dependent statement here that I hope Anna Maria will clarify. But yes, there's always some, this is an integration constant that is actually more like the value of the potential at infinity, which you cannot fix by any physical principles.
But optically, you can fix it.
Yeah.
You cannot force it.
Yeah.
Even, you cannot fix it. Not even inequivalent.
No, I think the integral of the radiation gives you the complete gauge invariant information you have at infinity. Yeah. Okay. So I want to say a few more general things before we describe the mechanics of constructing these vertices and understanding what it means for the interaction. The statement is that, so what do we know experimentally about this idea of causality? So we see it at vastly different length scales. And the place where you would think it's most obvious to check is long distances. And indeed, we see it very clearly at long distances, where you can have, imagine, where macroscopic violation of this are not seen. So I think good examples of this are, well, for example, gravitational waves that were emitted from this famous event. We have a gravitational wave and photons, which basically arrive from the same event that was like 100 million years away from us, and they travel through all that distance, and they basically arrive at the same time here. They don't quite arrive at the same time, but the difference of like hours we understand from is consistent with what we understand about the dynamics of the process, which produce these things, and it's nothing to do with the propagation. So basically, after traveling millions of years, it just added together to us. Like clearly, nature didn't want this information to get instantaneously to us, right? It's not violated. Okay? the other situation involving, for example, supernovas and neutrinos, where you see neutrinos just a little bit before the photons, exactly as you expect from the dynamics of the exploding stars. Okay? So violating this sending information faster than light does not seem to happen on these large scales. It's also seen at very short distances. And this may be a little bit less familiar. So what would you say is the most experiments that probe causality at the shortest possible distance? Yeah, what distances we probed it in experiments? Yeah? Yeah, so how do particle colliders test causality? Yeah. Question, yeah?
You could like produce photons and also the baryons, but then the photons have to move faster than the baryons.
Yeah, but then you'll have to time them to the typical time scale in the proton-proton collision is 1/10 TeV, which is 10 to the minus 27, 29, whatever second. We don't have clocks that precise, so we don't actually clock the RL time that precisely. We do have some resolution about the displaced vertices, but it's not timing. Yeah.
I guess, like in quantum field theory, you check causality by checking that the actual you don't have effects happening outside the light cone that actually
Yeah.
are cancel each other, and so
Yeah.
you can actually describe this with quantum field theory and check these fields.
Yeah. Yeah, exactly. Yeah. So one of the things so the part of the answer here that was given is that in quantum field theory you have this rule that space-like combinators vanish, so we can't influence things outside the light cone. And this statement, we'll actually discuss this more in 2 lectures. This statement is closely related to the fact that every particle in nature needs to have an antiparticle with the same property. So by checking that antiparticles and particles have the same properties, you indirectly checking causality. So this is our indirect check. So particles versus antiparticles. They have the same mass, opposite charges, all of these things come out of these type of arguments. But yeah, and more broadly, I think this is another answer that was alluded to, just the fact that Feynman diagrams work. That's just it. So that basically tests perceptive QCD works, or let's put it like this, QFT works for the standard model. And to me, that's basically indirect evidence, but pretty solid indirect evidence that nature doesn't violate causality at distances order 10 to the minus 20 meter, which is the inverse of 10 TeV. Okay? A scale with probe at colliders. Okay? If there was some new bump or something that did not represent the particle, like we'll just see this. Okay? So, and I think this number is important because relativistic causality is often motivated in textbooks by thinking about the grandfather type paradox, like macroscopic violation, you're moving very fast and you have a time advance, and then in some other frame it looks like you're going back for many years, backward in time many years. But nature doesn't only seem to prohibit instantaneous action at a distance over macroscopic distances, but also for these tiny distances. So somehow nature really seems to care.
Maybe another argument for why nature seems to care is these quantum protocols, right? Somehow usually you can do teleportation, but you can't really, you can show that there's no information change. That also
Okay.
is like a way
Yeah.
nature seems to care.
yeah. So this comment is about quantum mechanics seems to somehow respect all of this. So yeah, in quantum mechanics you can have entanglement, which allow correlations between systems that are far away, but they never allow classical signal. So what I mean by that also refines a bit what we mean by signal in. We mean really transfer of information that entanglement or correlations do not achieve. Yeah, thanks for the comment. And actually, here's a interesting anecdote. None of you probably know this story. Were around during this story. There was a experiment in the. So it all works until it doesn't. So there have been like experimental hints that it doesn't work. So there was a famous experiment by Opera in 2011, where they had a neutrino factory. So it's a beam that you send through a wall, and the beam dies, but the neutrinos keep going. And there was a neutrino at CERN, and they timed the bunch. They really timed precisely when the bunches were sent into the wall. And then they were measured in a mine a couple hundred kilometers further, Gran Sasso, in Italy. And they were found that they arrive 60 nanoseconds faster than you would have thought if they had moved at the speed of light. And that was a big deal. Because we care, not just nature, we care about this. Like the 60 nanosecond, like, is a big deal for modern physics. Right? If true, there have been a big deal. But you know, these experimenters are very serious people, and they say maybe we made a mistake. They went around and they checked everything, and they asked people, and they were very productive, very constructive. And actually, it was, of course, many theorists jump on this, and that's fine. But actually, some of the most memorable theory that came out of this era was there's some very nice paper by, I forgot the name. I think George. Sorry, I will not name the authors. I don't remember. There was an observation made that if the neutrinos were actually moving that fast, when they were moving inside when they were moving that fast, there's a possibility that they could Cherenkov radiate. They would actually be, the neutrinos had enough energy to actually be moving faster than the speed of the electron at that energy. So they could radiate they could Cherenkov radiate very efficiently an electron-positron pair that would basically deplete the neutrino beam before it arrived at the detector. And we know very well the speed of the electron at these energies, basically because the LEP collider worked. Okay, so there was a direct contradiction with other experiments. So I think it's a good lesson there. As theorists, we should be open-minded about. It's very important to be open-minded about new experiments which challenge our understanding, but we should also be exert some judgment and be critical and be skeptical of new things. Okay? So in this case, it turned out to be a loose cable. I mean, 16 nanoseconds is like the time it takes to like go 20 meters. It's very like, you have to use very precise GPS measurements to synchronize your clock to that. And the loose cable created a reflection in one cable, and the clock was synchronizing to the bouncing signal instead of the original signal. Life is really painful. Yeah. Okay. Another thing I want to say about theories, okay, nature really seems to care, and okay, let me say one thing before. I'm just going to erase this board. Is that okay? How precise can we state it? So in quantum field theory, we can state very precisely the statement. So in QFT, we have this statement that commutator are zero space-like, and like in QFT, this is it. Like this is an exact statement of causality, and like that's the definition of causality, done. Okay? Very clear. When you go to more theories that are a bit less understood now, like quantum gravity. So about quantum gravity. In quantum gravity, it's there are situations where actually we do have a sharp statement. So one example is quantum gravity in ADS. Because then you have this vanishing commutator at the boundary that you can do, which basically means that you cannot move faster to the bulk than to the boundary. And that's an exact statement of causality in quantum gravity with ADS boundary conditions. So that's a powerful statement. Something else which is safe is in Minkowski space with at least in d greater than 4, where you don't have IR divergence. You can use the S matrix. And you have statements, roughly speaking, that this field at the null infinity commute with each other. So impose this at the asymptotic boundary. That's pi plus. And so in these two cases, you have an asymptotic boundary where you can impose very precise statement. But in another situation, what you would really like to make is to make some kind of bulk statement. And we don't really understand how to state causality very precisely as a statement in the bulk, which we may have to have. Well, mathematically, we may have to have if our universe doesn't have an asymptotic boundary like this, if it's an expanding universe and so on. But also physically, like I don't care actually what the asymptotic of my universe is. Like I do experiments here. I would like to have a statement here, and we don't really have a good statement of that. Yeah.
Perhaps I just need to get back. Why causality in the boundary implies causality in the bulk in these two examples?
It's a very good question. And I will answer. So the question is, why does causality in the boundary implies it in the bulk, in the ADS-CFT correspondence? And the clearest cartoon for that, so I can draw it today because today I'm just drawing cartoons. Okay, is you imagine this is a cylinder, so you have a CFT at the boundary, and this is the ADS is like the metric geometry that fills the interior of this kind of soup. And the thing is that on the CFT, it's an exact statement that you cannot travel faster than the light cone at the boundary on the boundary of this, right? So here the thing should commute if you're slightly below the light cone. On the other end, imagine you had instantaneous action at the distance in the bulk. Then you could send a signal to a bulk point here, and then have an instantaneous action here, and then you would end up at the boundary faster. Because the ADS geometry, it's not obvious, but the ADS geometry has this property that it's kind of critical. If you take empty ADS, it takes exactly the same amount of time to cut through the bulk than to go around. So if you have a slight bit of interaction that is give you instantaneous action distance in the bulk, you will violate boundary causality. So yeah, so it's an exact statement and it's a powerful statement. Yeah.
So in the ADS, I just want to ask if I have some energy in ADS, which way does this form?
Yeah, if you put some energy in the ADS, everything acquires a time delay. Yeah. And the statement, it has to do that, otherwise you will violate the boundary causality. It has to do that. Yeah.
I think that the formal statement is that our world here
Yeah.
some energy.
Yeah, exactly. So in classical relativity, it's a theorem you can actually prove in the bulk in terms of called the Caron-Huot theorem. But the thing is that in the CFT, it's just an obvious statement. So the Caron-Huot theorem is the first indication that the DSCFT makes sense. But on the boundary, it's an exact non-positive statement.
You can also go above classicality, which is like the ANEC.
Yeah, exactly. So we can try to refine this with various bulk statements and focusing statements and bulk ANEC type statements. Yeah, which as far as I understand, the bulk ANEC is the status of it is that we believe in true because if you can do bulk quantum field theory, it should satisfy the Inek in the bulk. But deriving the bulk Inek from the boundary is not something that actually has been done. It's an open question. Probably Tom Hartman will talk about this. Okay. And okay, let me come back here. And the other thing that I want to say, because I want to provoke Toph, is that in science we always talk about testing hypothesis and having some alternative theory, and the thing about causality is there's no alternative, actually no predictive alternative. Okay, and just to make this point, I'm going to make a very extreme statement, but a very extreme example. Suppose we want to describe a quantum theory of gravity, and I don't care about not having incidence action to distance. Then it's very easy, right? You can write h of quantum gravity, put a little subscript qg, and your Hamiltonian would be like a sum of kinetic energy for all particles you have in the world, plus a pairwise potential that is minus gm m over r. Like, this looks dumb, but like, this is quantum mechanics, this is gravity, what more you want? And it's renormalizable, it's beautiful, it describes a lot of experiments. Okay, it doesn't describe gravity waves, but you can add this by hand. It doesn't describe, creation of particle, antiparticles, you can add this by hand. You can add things by hand to this model to fit all of the observed experiments up to whatever scale we've probed in experiments, and then do any crazy stuff you want just after. If you relax this principle of no incidence action distance, you can write anything you want, and nothing is particularly believable. So I think it's a very open question to like have some kind of credible alternative to assuming. Assuming this, that's not just curve fitting.
But now I'm slightly confused. The first statement was we don't have a good statement in the bulk.
We don't have one good now, but if we give up, then like that's basically saying that we cannot make any prediction past when this breaks. So there should be something better we can do, but I don't know what the principle is. It's a really completely open question. Yeah. Yeah.
On the one hand, you want a bold statement. On the other hand, if you have dynamic gravity, like you can certainly like how do you get things that are difficult to
Yeah, that's a part of the question. So the well-defined challenge is the following. So the question is, how do you make something that satisfies diff invariance and all that? So that's part of the question. So make a statement that makes sense for a bulk observer, that is diff invariant, everything you like, and allows you to retain the predictive power of this notion. Yeah. I don't know how to do that. So that is it. So I have half an hour left, is that roughly? Yeah. Good. That is good. So next I want to go a little bit more into the, start writing down some actual formulas. And the main formula I want to write down is the formula for, we'll do a simple example of a scattering amplitude that is mediated by gravity. So we'll do scalar scattering with a graviton exchange. And many of you will be familiar with this, and many of you will not. So I just want to get everyone on the same page. We can read this and see that what's the physics in it. Okay. And yeah, we'll do it in the S matrix or scattering amplitude language, because this will be the main language we use in these lectures. The general idea is to try to phrase these constraints in terms of observables. So the general statement is that if you just say these words, you have a massless spin 2 particle, you're forced to have gravity. Theory of a massless spin 2 particle. You don't have to say anything about matrix, path integral, nothing. You can derive essentially all the phenomenology of gravity using that statement. So I want to explain how that works. Okay? So the simplest observable we look at to explain the statement will be the scattering angle or deflection angle and the idea is you throw some two scalars at each other. So this would be the x direction, this would be the y, so this one is z, and the y direction. And we throw these two particles, and they're separated by some impact parameter p. And they can interact by exchanging a graviton, and that's supposed to give them a force that's supposed to deflect them. And it's supposed to be attractive, so we'll try to draw it the right way. Okay? And the observable is that after they scatter, what is the deflection angle as a function of the center of mass energy of these two guys and the impact parameter. Okay? So if you do this experiment, clearly by measuring the deflection angle, you learn something about the force. Okay? So it's the most, it's the first way historically we measured force within planets was by doing bound orbits, not scattering orbits, but it's still very similar. Okay. So the thing we will need to do that is a scattering amplitude for scalars. So we call this P1, P2, and the final state will be P1 prime and P2 prime. We'll work in the center of mass frame, so they're all like back to back. And so our first basic important thing is that the fact that we're going to go to a large impact parameter B, we're going to look at this at large B. And the amplitude at large impact parameter will be related to the fact that we have a 1 over, so we're going to momentum transfer. There's a pole in the momentum transfer variable in the amplitude. Okay? So if I draw this as a Feynman diagram, I'll draw it differently. Looking at this graph, P1, P1 prime, P2, P2 prime. This Q equal P1 minus P1 prime. And this amplitude is going to have a pole. And it's only this pole that's going to matter, because when we go to impact parameter, we'll have to do a Fourier transform from momentum to position space. And the thing that's going to give us something interesting at long distance is going to be this pole. Okay, so we just have to please buy this for the moment, so we'll come out of the equation soon. Yeah. Minkowski space. Yeah, exactly. So we're assuming a Minkowski space. So this idea of causality that things have to factor into emission and absorption of particles should be completely general and work in any geometry if we can make it well defined. To whatever extent we can make it well defined. And here I'm going to do it in Minkowski space because I can use symmetries to constrain what these vertices look like most efficiently. Okay. In general, you still use local Lorentz invariance or something. It's just Minkowski space will just let me do the calculation. Okay. Yeah. So exactly. Yeah. M. Yeah. Yes. Yeah. And yeah. So it's related to pole in M, which is the S matrix element between P1, P2, and P1 prime, P2 prime. Right. So we're computing some element within some initial state, time evolve, and final state with the S matrix. Thanks. Yeah. So we're in Minkowski space. Okay. So, as I mentioned, the sort of interesting thing about these, there are two ways you could go around this calculation. You could start from your favorite action, say the Einstein-Hilbert action, couple it to a scalar, derive the Feynman rules, and do calculations. You could do that. We will not do that because, in fact, the answer is completely determined by this kinematical statement. And this is what I want to emphasize here. Okay? You don't actually have to know the Lagrangian. Just knowing the symmetries of the particle you're exchanging tells you the answer. Okay? So why is that? So the fact that this spin 2 means that this vertex, so I can break the calculation into, so the fact that I'm going to this 1 over q squared pole means that I can break the calculation into some vertex here. 1, 2, so it'll be some v1 mu nu that describe this. Spin 2 means it has a 2-index tensor. So I have somehow 2 indices here. And then I have some other vertices here. And between them, I have some propagator that I will describe in a second that somehow ties those indices together, and a propagator. Okay? So this is m at low energies, and q squared go to 0. And because I'm only going to be interested in this pole, I don't have to worry about other diagrams. Okay? So I'm going to describe this ingredient in turn. And it claims that they're just determined by symmetries. So no, it comes from a propagator in Feynman. I'm assuming it's something like Feynman rules work. So the Feynman rules allow you to have some denominators, and by Lorentz invariance, they have to be like q squared. And the definition of a massless particle is at 0. Yeah. So all I've used so far is something that is in this statement that I'm gradually unpacking. Okay. Right. So from this matrix perspective, exchange of a massless particle means you have this pole times something. Now, so what is this thing here? This propagator here? What is this numerator of the propagator is supposed to be a sum over all the possible polarization of this thing, and these polarizations have to be traceless. And for a massless particle, the spin refers to a SOD minus 2 E-rep. And then for each of these SOD minus 2 tensor, we associate the polarization. And then with lambda bar, complex conjugate, with lambda star together. Okay? So I inserted complete basis of these tensors, and my propagator must take this form. Okay? So yeah, SOD minus 2 is because that's the little group that is relevant here. Yeah, so there's a subgroup of, so the question is why SOD minus 2 is a subgroup of SOD minus 1, 1, the symmetries of d-dimensional space-time, that preserves a null q mu with q squared equals 0. Okay? Actually, the subgroup is a little bit bigger, but all the finite dimensional representation, we're going to be assuming that we only have finite dimensional representation in compute. All the finite dimensional representation have to do with SOD minus 2. Yeah.
Are all these statements perturbative statements?
No, so far it's all perturbative. Yeah. The motivation for this, there's a self-consistent justification for this, which is that we're taking large impact parameter B, and by dimension analysis, the coupling constant of gravity makes gravity weaker and weaker at long distances. So in this limit, this is a legitimate approximation. Yeah, loops are suppressed in the limit that I'm considering. Yeah.
Are you already assuming that your particle doesn't have any other internal freedom like charge?
Yes. So here I'm assuming. So the question is, am I assuming that the particle has other quantum numbers? For the moment, yes. So for the moment, it's a bare scalar with nothing.
Oh, no, I mean
The mediator, yeah, the mediator is a single graviton. You could try to generalize this by having multiple gravitons. It turns out that it doesn't work. It can only be one graviton, but that's a more advanced statement. So first, let's understand exchange of one graviton. Okay. So the fact that it's SOD minus 2 tensor means basically that we have to find a way of embedding these things into space-time. And so when we have to do it in the Lorentz covariant way, so the way to do this is that, well, you have to, these indices run from like, these are d-dimensional indices. And this is like d minus 2 dimensional. So you have to somehow map a way, find a way to embed a subspace, which physically represents like the transverse plane, like a transverse polarization of the graviton in 2D dimensions. And the way to embed the subspace in the Lorentz covariant way is that to embed it in a way that satisfies this constraint. So this polarization needs to be orthogonal to this vector Q. Okay? This is needed to embed SO d minus 2 into, okay? So you need that. Now, if you think about the vectors that are orthogonal to a vector Q mu, a null vector Q mu, one solution is epsilon proportional to Q, and the other options are transverse. So it's kind of a launch null and transverse part. Epsilon is proportional to Q mu, let's call it some psi nu, or fully transverse. Okay, so we have these two options. Now there's something very funny about this launch null mode. That this launch null mode, when you try to compute the norm of this mode, Q here, this psi has to satisfy Q dot psi is equal to 0, and Q squared is equal to 0, and therefore this launch null mode satisfies epsilon squared equals 0, which is like a 0 norm state. And in quantum mechanics, if you have a state that's 0 norm, it's better to do nothing. Because adding this state to another state should do nothing, right? So must decouple. Okay? So that actually is a constraint on the thing that this propagator is dotted into. In order for this 0 norm state to decouple, we absolutely need this vertex that satisfies Q times Z1 mu nu equals 0. It's needed. Okay? So this is known as the word identity or conservation law for the source. But we see that it's needed because otherwise we have a launch null mode with 0 norm that would be source, and it's just sick. Like there's no Hilbert space interpretation of this. You cannot have a positive Hilbert space interpretation of this thing. It has to be H mode. Okay? In other words, you need the equivalence relation that epsilon mu nu is the same as epsilon mu nu plus Q mu psi nu for any psi. Okay? So you need this equivalence relation for polarizations, which implies that the thing they're dotted into satisfy this constraint. Okay? So this should be familiar, but I'm just explaining how this derives from just Lorentz invariance generalities. Okay? And then once you have V's that satisfy this constraint, with no loss of generality, this sum you can do, and it's just going to be a projector that sets eta mu, that's a Minkowski metric, mu prime, sorry, mu prime, mu prime, symmetrize, plus eta mu prime, mu, mu prime. And the fact that it's traceless means that the sum of polarization has a 1 over d minus 2. That number is important. Times eta mu nu, eta mu prime, mu prime. Okay? So based on symmetries, the propagator of a massless spin-2 particle has to have this. And this guy here is a trace subtraction. Yeah.
Why did absolute imply that QE is equal to 0?
Yeah, thanks. It's because, okay, I need this equivalence class because these type of polarizations have 0 norm. Okay? So once you accept that the polarizations have this equivalence relation, then we need, for the pairing V mu psi mu nu to make sense under this equivalence class, you need, so we need this plus Q mu psi nu equal V mu nu psi mu nu for any gauge equivalence psi nu. So we need this relation to hold for any gauge transformation psi nu. And therefore, the only way this can hold is that this times this is 0. Yeah, that's a very important point. You could add terms that depend on Q. These are choices of gauge. But with no loss of generality, because Q dot V is equal to 0, I can drop these terms. Thanks. Okay. With no loss of generality, yeah, modulo Q mu terms, which don't matter. Okay. So that's a propagator. And then I'm going to move all the way here. All we have to do now is to enumerate the possible vertices. So V1 here is a function of mu nu. So it's a function of this graviton Q mu, which is a momentum Q, momentum P1, P2. P1, P1 prime, sorry, and Q will be P1 minus P1 prime. It's a function of this data. And this vertex needs to be symmetrical in mu nu and orthogonal to Q mu. So we're just going to enumerate these things. So in general, without doing any work, you would say, and there's another thing that, if I come back here, will become clear. The other thing that's also true is that the vertex is orthogonal to Q, but the vertex is also defined modulo Q, because if I add anything proportional to Q, I'm going to put it there, the Q is going to hit something else and give 0. Okay? So anything proportional to Q does not matter. Plus Q mu C mu. Since this cancel in V by V. Okay, so it will not contribute, so I don't care. Okay. So we can make the most general ansatz. So the most general ansatz will be that using Lorentz invariance will be V1 mu nu. It could be some coefficient. I'm going to call it kappa times P1 mu, P1 mu. That's an option. I could also have something like maybe kappa prime, P1 mu, P prime mu. And then maybe something with P prime, mu, and maybe something proportional to eta mu nu. Okay? I could have all of this. The thing with these games, you always have to think twice whether you included everything. It's not as straightforward. This is a game of enumerating everything you can write down, but you understand the game. And so I'm just dumbly writing down. But then notice here that P prime is equal to P plus Q. and I told you that Q doesn't do anything. So actually, this is stupid. This does the exact same thing as this guy. So this is not needed, and this is not needed. And adding these things is equivalent to putting this guy with k kappa plus kappa prime prime coefficient. So I'm just going to keep the first term. Yeah?
So here, like you have P1 new, P1 new.
Yes.
And the second term is P1, P prime.
Yeah, exactly. This one has P1, P1, and this one has P1, P1 prime.
Ah, okay, P1.
Thanks. Yes, there was a prime missing.
These are
Yeah, they're all P1s. Great. Thanks. And something else which you can show here is that this guy actually does solve the constraint by itself. And you can show Q dot P1 is equal to just complete square is something like P Q plus P1 square minus Q square minus P1 square over 2. This is 0 because we want to be on this Q square equals 0 pole. And this is the mass of the scalar minus the mass of the scalar. So that's 0. The scalar is the same. In the exercise, you would check what happens if they're not the same.
But the
Yeah.
one of the terms can be off shell, right? By taking the vertex, do we want all the three because it's finally going to be.
Great question. So this is on shell. This is on shell. So P1 square. I'm going to use mostly plus metric. So this is 0. And P1 prime square plus M square equals 0. Now you're asking, a priori, normally in the final rules, this guy would be off shell. However, in order to calculate the force at large impact parameter, I only care about the pole in this expression. So in the numerator, I can set Q square equals 0. Yeah. So this will come momentarily, but when I do a Fourier transform to go from Q space to B space, anything in the numerator, the Q square, will cancel the pole and give me something that vanishes at large P. Okay? Yeah, exactly. If you wanted to know the possible contact term in the force, you will need to keep this. So this Q square here does not contribute at large B. So yeah, so the comment was if you wanted the force if you wanted to know all delta function term in the force, you will need this term. Do not contribute at large. All right? And this term here is not transverse. So this guy is transverse. This guy is not transverse. So basically the answer is that V1 is equal to kappa P1 mu P1 mu. There's no option, no other option. Okay. And now we can ensemble this, and we have our scattering amplitude. P1 prime goes to, sorry, P1, P2 goes to P1 prime, P2 prime. You just multiply all these ingredients. There's a kappa square, 1 over Q square that I had before. Then the product of these V's times projector. So it will give me a P1 dot P2 square minus 1 over D minus 2, P1 square, P2 square. Plus no 1 over Q square pole. Okay? Yeah?
Why can we assume kappa is like a constant rather than a function of momentum?
Ah, that's great. This is constant. So a priori, kappa will be a function of momenta. But all of the dot products between the momenta you can write in terms of momentum square. So kappa is a function of P, is really only a function of P1 square, P1 prime square, and Q square, which is a function of M square and 0. So I'm going to treat this as a constant. Okay? There's nothing it can depend on. There's no Lorentz invariant thing it could depend on. Okay. And now, so the claim is that from this function, we can understand the deflection of a particle, say in the non-acidic case, say planets deflecting around each other, as well as bending of light by the sun by taking a limit where it's very fast. So I'm going to explain that this formula interpolates between light bending and planet scattering. Okay? Actually, I don't have a lot of time, so let's see. Maybe yeah, okay, I think it's actually I think I will do it next time. Let me see. I can probably write one for. Let me find a way to wrap up. Yeah. So I want to do this sort of calculation in detail, and next time I can probably sketch the one thing that will happen, and the basic thing we'll do is that we'll introduce a state B that has a localized impact parameter, and then we'll compute the S matrix acting on B, and we'll find that basically it goes to 1 plus I times delta tree level, it's a function of S and B, where this phase shift is just the Fourier transform of this thing. So this is very kinematical. B minus 2 Q perp over 2 pi B minus 2. So there's nothing deep here, but in terms of kinematics, I'm saying that the impact parameter is Fourier conjugate to the momentum transfer. Okay, and that's something that's very intuitive and is true at large distances. From this, and then can compute that, and then there's a tree-level amplitude that we have here above, which is really just a function of center of mass energy and impact parameter. And there's a kinematic factor that I will skip here. It's a 2E1, 2E2 times the velocity dependence in this. It's kind of a kinematical factor that converts the amplitude in relativistic normalization to a phase shift. So just all of this is just kinematics. And then the point is that we get the momentum transfer. So what's the momentum transfer? Is that this is our final state. Our final state after evolving our initial state, that a two particle going as an impact parameter is this final state. And what we want to calculate is the momentum transfer, delta P, which is the expectation value in this final state of the momentum of particle 1. Okay? Minus initial. Okay? You can calculate this thing, and P will turn into minus I d over dB. So this thing will turn out into simply into the derivative of the phase shift. B of delta of S B. Okay, so that's an important formula, and this is true to leading order in a small angle. So let me recap. The next step to interpret this result are just purely kinematical. You do a Fourier transform to go from momentum space to impact parameter B, and then you take a derivative of the phase shift to get the momentum transfer. It's a very classical relation. Okay, and actually Sébastien Misère will discuss this much more precisely, and also explain to you how to go beyond the leading angle approximation. I'm just writing a thing that should be relatively intuitive, or at least easy to accept. And the point from this is that by calculating this at low energy, you relate this coupling constant to G Newton, 32 p G Newton. So a priori, this constant K had no physical meaning. It was just an unknown constant in the three-point coupling. But by comparing the prediction for the deflection angle of a slow planet, you get, and comparing it with the prediction that Newton made, you can fix this coefficient. And once you fix this coefficient from an experiment, this formula at the top gives you the full energy dependence of the thing. And one of the highlights, which I can finish in 30 seconds, is that in d equal 4, you see there's a 1/2 on the second term. So this formula has two limits. So if I take p1 dot p2 square minus 1 over 2 p1 square p2 square. So it has two limits. So in the non-relativistic limit, all the p's are equal to the mass, and they're in a time direction. So this is equal to m square minus half m square. So it's half of m1 square m2 square. And when you take the high energy limit, so if you have a photon scattering against the sun, which has a mass, and a photon which has no mass, and this term does not contribute, and just have the first term, and you'll get m sun square times energy of the photon square. Okay. And this famous half is the famous statement that the light bending in Einstein's theory is twice that you get in Newton's theory. Okay? So bending in GR is equal to 2x the Newtonian prediction. And that what we're seeing here is that this all comes from the fact that we say that this graviton is a spin 2 particle, and therefore its propagator at minus 1 over d minus 2 subtraction with transverse modes, so subtracting the trace. Okay, so it comes from saying that the graviton has spin 2. Okay, so that's the first one of the things you observe from this calculation. So this partial prediction of Einstein's theory we see is contained in this statement. So actually, the rest of this problem, it will be in the homework. It's just kinematics. And next time, we will discuss more prediction of Einstein gravity, how they're encoded in the amplitudes. Sorry, I'm slightly over time.
All back at 2. I'm counting on the students to make sure the new lecturers know where to go for lunch. So please escort them there. Thank you.
Sorry. Could you pinpoint in what specific step of the calculation causality in terms of, oh, your particles cannot travel faster than light?
It was at the starting point, so I assume that
But what if you were not looking at this leading order and then you would consider some other channels and so on? It's just the thing that all channels you will have to basically factorize, right? Even, let's say, if you had a channel like this, right? Some
exactly.
X or U channel, right?
So the absolute is to factorize in our channels. In the Parkstar here, what we're using is a bit different from the usual Kotkowski unitary rules,
Right.
because we're already cutting in the T channel.
Yeah.
We're saying that things have to factorize in the T channel.
Yeah,
But they do have for causality to work.
Right, okay. And then if you wanted to go to subleading orders in B, you would consider something like a loop here.
Yeah, exactly. Yeah, because the expansion, because the dimensionless and parameter turn out to be something like this.
Right.
So if you want to do to subleading order, you also need to include one more parameter.
Okay, right. That's how you see, oh, sorry. That large B corresponds also to the expansion in G. Right.
Can I ask a question? So you derive that. They go very smooth. Why doesn't what is this doesn't depend on epsilon? Because if it doesn't depend on epsilon, it doesn't transform.
Yeah. We can do two things. So I can put it with indices, or you can also define a polarization that depends on p's and epsilon to be this times epsilon mu.
Oh, you subtract that.
Yeah, exactly. And usually what people do when you're talking about a massless symmetric tensor is that you write it as a product of epsilons, because then this polynomial in epsilon has all the information.
Okay, yeah.
So I didn't want to introduce an extreme notation all in one lecture, but yeah, this is what professional will actually do.
Number of questions, I guess, about that derivation that makes sense. I tried to address this in the lecture, but I didn't quite understand. So we're considering only in the limit of large B.
Yeah.
Why does that? So how does that affect essentially the fact that we're only looking at this diagram?
Yes, that's a very good question. So the thing that happens is that actually Sebastian will talk much more about this, but so the answer that come out for the here it turns out to have an extension in this dimensionless parameter. So if you wanted to go to the next term in 1 over b, so there will be two types of correction. They have to be dimensionless, and this is dimensionless. So the next thing actually would be gm over b squared. You will have also things, you can also do this 1 plus 1 over b, but this will have some kind of a h bar. So you have two types of correction. You have correction that are quantum mechanical and may or may not matter depending on the situation, and this type of situation. And to account for this thing, you will still be able to have this slogan that you can understand everything from all forces from exchange of particles. But now you need to account for graphs where you exchange two particles. Because each of these vertex, so this is G, each of these vertex is square root of G, and with 4 of them we can make this. So large B suppresses this diagram.
So you don't, in order to get this extent, you still don't need to know anything about like the Lagrangian of the theory?
No.
Because this is, I guess, just
No.
you're assuming there's gravitation.
No, exactly. But the thing you need to know is the units of G, which is mostly what we use when you use the Lagrangian. Yeah, the units are important to really